thank you guys for coming to my presentation today. We're going to do a crash course on how to develop on L1, on Bitcoin's layer one. There's a lot of stuff you can do there, and so I'm going to teach you all about some of it today. With this presentation I made called Bitcoin Script, the world's first smart contracting language. Okay, so let's get started. If you want to follow along, which I recommend you do, you can pull up this URL right here. In fact, let me show you what happens if you do. If you just take this, which I will drop into the chat, and paste it into your browser, it'll just take you right to this presentation. And I recommend you do that. Recommend you do pull this up. So let me put it in the chat, because link to the presentation. I recommend you do that because we're going to be doing a code along here, and you're going to be building your first Bitcoin smart contract with me today. Like, this is going to be, if you've never done it before, this will be your first time, and you can do everything. You don't need to download anything new. Well, you do need Bitcoin. Other than that, you got everything you need. So the other thing we're going to do, I want to bring up this GitHub, which is called Learn Bitcoin Script. And I want to show you what we're going to build today. The final product that we're going to make is right here on this page. And look at this. Isn't this gorgeous? This is the perfect application. Just a blank page with no errors anywhere. No, everything that's in here is happening in the browser console. So if you go and open up your browser console right here, you can actually see some errors. There are some errors on this page. That's not good. What's going on there? Well, friends, we may be having a wonderful time today because unexpectedly the demo's not working, but we're going to build it together. What's supposed to happen is it's supposed to create a smart contract address where an oracle can decide who gets some money in a contract about a ball game. So we're going to build it today, and we'll find out why there are errors, which I will fix after this show. But in the meantime, you can pull that up, and then also I want to mention an IDE, an integrated development environment for interacting with Bitcoin, is on this page, and you can switch from Liquid over to Bitcoin right there, and then you can actually play around with like doing stuff with Bitcoin Script. So you can add numbers. And you can do, op add to see what that looks like and stuff like that. And I would actually take the number 1, add the number 2 to it, and get 3 as a result. So you can kind of see some stuff happening there. We're going to be using that later in this thing, so you might want to pull those things up. But once you all have that ready, the next thing we're going to do is we're going to download Bitcoin Core. We're going to download Bitcoin Core so that we can create. So that we can use it, use a little Bitcoin testnet on your own machine to create a Bitcoin smart contract together. So I recommend you go, I'm going to show you how to do it. This will be different on different machines. If you're on like a Linux machine like I am, it'll be how I'm doing it. But if you're on a Windows or a Mac, you'll use those buttons. I'm on Linux, so I'm going to download the latest version of Bitcoin right into my downloads folder. And then as soon as that is downloaded, it's called Bitcoin 25. So I'm going to go in, I'm going to open up my terminal, go into my downloads folder, go into Bitcoin 25. Oh, I got to unzip it. In Linux, we use tar instead of zip. Well, sometimes we use zip, but today I'm using tar that's an equivalent of zip. So I just unzipped that directory. Now I'm going to remove the tar file or the zip file, go into the Bitcoin directory, and we've got a couple of subdirectories in here, including bin, which is the binaries or the actual program, a configuration file, and some other stuff. I'm going to go into the bin folder, and this is the one I want, the one that says Bitcoin Qt or Bitcoin Qt. That is a graphical user interface for using Bitcoin. And you can just run it using these flags. So if you're on Windows, the procedure is going to be a little bit different. You'll probably not need a zip file. You'll just be able to download the application right away. And I think in order to make it run in reg test mode, that'll put a testnet on your machine. I think you'll have to like modify the desktop icon. But yeah, you can just Google how to run Bitcoin in reg test mode, and follow the instructions if you want to follow along here, which I recommend you do, because we're going to need Bitcoin to do this. And it's better to use it on a testnet than use it on the mainnet, where it costs a lot of money to do this stuff. I'm also going to run it in daemon mode. I'm going to turn on something called TX index, which indexes all the transactions that they're created, makes it easier to program. And then we'll just run it. So this is what it looks like when you run Bitcoin. This is a fresh new installation of it, and it says, welcome to Bitcoin Core. It invites me to choose where I want to store my data. I'll just use the defaults. And here I am with Bitcoin running in reg test mode. You can see how it says right up there, reg test. I've got a little testnet on my machine. It says that it thinks it's 12 years ago. It thinks Bitcoin just started. You know, it thinks it's January 2009. But we can easily go into our console and well, actually, we need to create a wallet first. Let's create a wallet called test. And then we can catch it up quickly by just mining a block. So I'm going to do get new address. There's a little address I got, and then generate to address, 1 block, bam. Now it's all caught up and it realizes it's today. So, and we've got 50 Bitcoins in our wallet right there. So I hope you all have Bitcoin Core running in reg test mode, because we're going to use it. I'm also going to generate 100 blocks, because you can't spend any coins until after 100 blocks have passed. So just generated 100 blocks, and now we're very rich, and we have loads of Bitcoin, loads of fake, testnet Bitcoin on our machine to use. 5,050 Bitcoins. Okay, so we've all got Bitcoin Core running. We're all ready to make a smart contract. I'm going to tell you a little bit about how smart contracts work in Bitcoin now. So what is Bitcoin script? Well, Bitcoin script is this wonderful programming language that was created by Satoshi for creating contracts in Bitcoin. It uses a concept called locking scripts and unlocking scripts to do, well, contracts. And these scripts are made of text. So ordinarily in Bitcoin, we think of, Bitcoin working like this. Bob here, he has some Bitcoins, right? That's what he's got. He's got some money, and he wants to send some of it to Alice. So he types in Alice's Bitcoin address, right? And he fires off some money, and that's it. The Bitcoin goes to Alice's wallet, and Alice has the money now. We like to think, that's how Bitcoin works, and that's how most wallets will try to present it to you, to make it seem easy and familiar, because that's how things like PayPal work, and that's how things like I don't know, Venmo work. However, as indicated by the X here, that's actually not how Bitcoin works. That is just an analogy or a visual attempt to emulate more familiar software. How Bitcoin scripts actually work, or how Bitcoin actually works, has a reversed flow. The first thing that happens when you want to send somebody money is that person has to create something called a locking script, which I represent with a little padlock over here. Usually it's their public key. They make a locking script that says only the person with this public key can spend this money. And so Alice over here, she's got her private key off to the side, and she creates this locking script, this padlock that she gives to Bob. That's when you show somebody your Bitcoin address, you're actually showing them a locking script. And then Bob's wallet will take some of his Bitcoins and snap that padlock onto him, right? It'll say, okay, these coins are locked to this little padlock here. And now, because Alice has the private key, only she is able to stick that in and unlock the padlock and free the Bitcoin so that she can spend them. That's actually how Bitcoin scripts work. It's the reverse of normal. Alice acts first. She creates a locking script. She presents it to you, and then you can send money. Well, you're not actually sending money. You're just locking it up so that only she has the key. But all of this, even this lock and key analogy, that's also just an analogy, right? There is no actual padlock. There is no actual key. Everything's just text. The lock is text. That's your Bitcoin address. Your private key, that's just text stored by your computer. But it's able to, your computer is able to run a program that can use this one piece of text to satisfy the conditions of this other piece of text. And it's kind of like a lock and a key. So that's what Bitcoin script does. Whenever we're making contracts in Bitcoin, you have to keep in mind, what we're doing is we're creating very complicated padlocks. We're creating very complicated padlocks with complicated keys. And that's what a smart contract is. How do we go from Bitcoin scripts to what we are more familiar with in terms of smart contracts? Well, so this comes from Nick Szabo, who is possibly the inventor of smart contracts. In 1996, before any of this stuff existed, he wrote about how we could do smart contracts if we had digital money. And he defined a smart contract as a set of promises specified in digital form, including protocols within which the parties perform on these promises. I always find this sentence of his a little bit confusing. The first part's easy. A smart contract is a set of promises specified in digital form. That part's easy. I get that because all contracts are promises. Like, I will do this and then you will get this result, or you will do that and then this will happen. They're always promises. But of course, a smart contract is a digital promise. We write it down on like a blockchain somewhere. So that part makes sense. It's a digital promise. But then this second part, including protocols within which the parties perform on these promises, that uses some weird grammar. I wonder, sometimes I wonder if Nick Szabo, English might have been his second language. But another way to express this is that software enforces the rules. Software enforces the contract. Your wallet will do it, or the network of nodes will execute the contract. So yeah, that's a smart contract is a digital contract, and then software that's enforced by software. The primitive ancestor of smart contracts, he says in the same paper, is the humble vending machine. And this is interesting. I did some research on vending machines in preparation for this talk, and one thing I found out is that the ancient Greeks had them. There was an ancient Greek inventor named Hero, I think it was Hiro, of Alexandria, and he lived in a temple. Well, I don't know if he lived there. He worked at a temple, and he made a vending machine. He took some holy water and he put it in a vessel, and he made it so that if you put a coin into this vessel, it would drop down onto a little plate, and the plate was attached to a lever, so it would drop when the coin landed on it, and the lever would move up and open up a valve, which would let some holy water out. But then, because it was tilted now, the coin would slide off of the plate, and a spring would go back up and shut the valve again. And so you'd only, if you put in a coin, you would get a little bit of holy water, and then it would shut off again. So it's interesting. The ancient Greeks actually had a vending machine. But what's interesting about them and why they're an ancestor of smart contracts is that in order to use a vending machine, you effectively you've created a promise. You've created a device that will enforce a promise. The promise in the case of a vending machine is like, if you put in the right amount of money, you will get your snack or your water. And that promise doesn't need a human to come around and enforce it. The machine itself, the hardware itself, the spring and the lever will enforce that contract for you. So that's an interesting property of these things. And what Nick Szabo envisioned was that a smart contract would take that same design, but make it so that software enforces the logic of the contract instead of hardware. And so that's the idea of a smart contract, is we want to create a situation where a piece of software will enforce a contract and cause something to happen, which is neat. So I want to use a little bit more. I want to go into this analogy a little bit more and apply it to Bitcoin, because a vending machine is sort of like a very complicated padlock. I mean, it's a really big one, but when you put something in a vending machine, it's kind of like putting it in a box that has a lock on it, right? Like most of these things, you can't just open the door and take them out. You've got to have the right key. But these complicated padlocks, the vending machines, the key is a little different. The key is like the size and shape and weight of a coin, and that key, you put it in, will then trigger a mechanism that unlocks like a portion of what's inside. It'll make one snack drop into the thing below, the unlocked portion. So if you think of a vending machine as a really complicated padlock, and a coin as a key that you can put into them, we can use that as an analogy for how Bitcoin smart contracts work. We're going to lock up our Bitcoin inside of a vending machine, and then someone else, Alice over here, she has to have the right piece of text. Didn't mean to do that. She has to have the right piece of text, the authorization or the ability to insert something into our little vending machine, into our piece of text, that'll cause our Bitcoin to become unlocked. So that's another analogy for what Bitcoins are. They are advanced digital smart contracts, or they're advanced digital padlocks for which there is a set of one or more pieces of text that can unlock them. Some of the things you can do with smart contracts in Bitcoin, the most common thing we do with them is we use proofs of purchase. This is the Lightning Network gives you a proof of purchase, for example, every time you buy something. So a proof of purchase works like this. You get a coin if and only if I get a receipt. And so typically I will lock up some Bitcoin into a thing that says, you know, the piece of text you have to supply me with in order to get this coin. It's not just your key, but it's also a receipt. You also have to say, you know, I owe you a piece of gum or whatever, or you have purchased a piece of gum. And once you stick that piece of text in along with your key, then the coin unlocks and you can get your item out. So proofs of purchase are pretty much the most common thing we use in Bitcoin for smart contracts, because you know it is designed to be a payment network, and that's a pretty important part. A very common thing you can do with them also is make tokens. In Bitcoin, one of the things you can do is, since you can put text on the blockchain, you can mark an address as being special somehow, and then treat the sats that are in that address differently. Like you could say any sats that go into this address are red coins. And so once I send them to you, you can actually track on the blockchain that these are red coins, and maybe they have some extra value. Like Tether did this with Bitcoin. They issued the first stable coins on Bitcoin by just marking an address as special, and then if they sent money to or from that address, they counted as tethers. And they would do like small amounts of Bitcoin for that. Another thing you can do is swaps. These are pretty common. You can, where I say you can get X amount of coin A if and only if I get Y amount of coin B. You can do that with tokens, but you can also do it with cross blockchain stuff. So you can make it so that like you have to put in the actual private key to some coins you hold in another chain. And then once you give me that private key, I can sweep them on that other chain. But simultaneously, by putting in that private key on Bitcoin, you also got the Bitcoins. So you can do cross-chain swaps as well as token swaps using the smart contracts in Bitcoin. Two other things you can do. You can do elections, ball games, and escrow. And this is actually what we'll be doing today. I'm going to show you how to build a ball game contract where we're going to have a guy up here, this little guy in green. He's going to be an oracle, and he's going to have a key he's going to know about an upcoming game between the Packers and the Saints. And he's going to create a key for each one of these. And we're going to have a Bitcoin locked up with 3 padlocks, one belonging to this guy, one belonging to this lady. And then the missing key is going to be provided by this oracle over here. So one of these guys is going to bet the Packers will win. The other one's going to bet the Saints will win. And you'll need 2 keys. You'll need, he will need his own key plus, the Packers key, and she'll need her own key plus the Saints key. And so then the oracle is going to reveal one of them and allow whichever one he picks to get the money based on whoever won the ball game. So that's the actual contract we're going to build today. But that's something you can do with Bitcoin. You can get a coin. You can make it so that you get a coin if and only if someone you trust says A, or I get a coin if they say B. We use that for escrow. We use that for, you could use it for elections and stuff. You'd bet on who's going to win an election. And then we have lotteries. Bitcoin can do random numbers, and since Bitcoin can do random numbers, you don't actually need a third party to do a lottery. You can just assign every player a number 1 through n, all come to consensus on what everyone's numbers is, and then they pick a number 1 through n and reveal it, and then you do some addition on these numbers and take the modulus, and then the winner is whoever's number comes up. So you can do lotteries and coin flips and stuff without needing a third party because Bitcoin can do random numbers. It's actually really good at random numbers. We do them all the time. We love random numbers in Bitcoin. They're everything. They're your public key, they're your private key, they're the block header. Bitcoin loves random numbers. Anyway, these are some examples of things that I personally have built. I've definitely built proofs of purchase, tokens, swaps, elections. I'm going to build a ball game contract with you today. Lotteries. There's a whole lot of stuff you can build just natively using Bitcoin. But let's talk about some of the built-in functions of Bitcoin. Bitcoin's programming language is called Bitcoin script, and these are not all the functions it has, but these are the ones that I most frequently use personally. I really often use the signature functions. Like that's how you ensure that only one person or only one from a set of people can spend some money, is by using checksig and check multisig. Check multisig also allows you to do stuff like voting, where you can have people vote on and only if 51% of the people say it should go here, then you have that happen. You can use check multisig for that. I love the password functions. I call them password functions. Normal people call them hashing functions. But you can take a secret and hash it, and then say, you can only spend this money if you know the secret that hashes to this value. I think of it as a password, essentially. You can only spend this money if you know the password to it. So I like those functions. We're going to use one of those today. We're going to use this one, hash 160. We have time functions. We have check lock time value and check sequence value. Those are check lock time verify and check sequence verify. Those both are forms of time lock. See, LTV is an absolute time lock, where you say something like, I'm going to put some money in an address and you can only spend it after January 1st. Like, no matter when I put money in that address, it's only spendable after January 1st. And then a check sequence verify is a relative version of that, where you say, I don't know when I'm going to put money into this address. It might be today, or it might be 3 years from now. But when I do, once the money goes into there, you have to wait 2 weeks. So you might be able to spend it 2 weeks from now if I put it in right now, or if I put it in 3 years from now, you'll have to wait 3 years and 2 weeks to spend it, because you just have to wait 2 weeks once it goes into the thing, once it goes into the address. So we have both of those forms of time locks. Those are pretty commonly used to make smart contracts. We have mathematical functions, add, addition, subtraction, checking if a number is greater than a number or less than another number. We have an equality checker, and this one also works on strings. And so not just integers, but you can also check if two strings are the same. We have stack functions. In Bitcoin script, stacks are kind of like arrays. If you're familiar, well, they're exactly like arrays. If you're familiar with, JavaScript arrays or Python arrays, stacks are the same thing. You can duplicate an element that's in an array. You can drop an element from an array, which would be its equivalent to pop in JavaScript. You can swap elements in an array. You can rotate them. You can shuffle things from the back to the front, or just move everything in a cycle. You can check how deep an array is, or how deep a stack is. We call it with the depth function. That's kind of like array.length in JavaScript. And in Bitcoin, everything goes onto a stack. There's nothing. When you use a Bitcoin script, all of your functions are on a stack, and all of the inputs to those functions also are on a stack. So everything uses arrays. And then we've got Boolean functions, and or not, NAND, NOR, XOR, and XNOR. These to me are my favorite Bitcoin script functions, because these are the building blocks of circuit boards. You can actually design a circuit board in Bitcoin script and run arbitrary computations on it. And I've done that. I've actually built circuit boards in Bitcoin script so that I could run arbitrary computations, which is kind of fun. The Boolean functions are great. And then we've got branching logic, if then else, verify, and return. Everyone should be familiar with if then else. That is known as AI these days. You just string together a bunch of if statements. I'm just kidding. That's not how they work. But yeah, if then else allows you to have branching logic, where you're like, if this condition is true, then run this set of this script, and if it's not, then run this other one. And then we've got verify and return. Verify says only continue if the previous function returns true. So you can write a function that does I don't know, a coin flip or something. And then you say only if the coin flip landed on heads, you verify that, and then you can proceed. If it landed on tails, or if it landed on zero, then you stop the script. And verify will do that for you. It'll make sure that the previous function did what you want before you continue. And then we have return, which is the opposite of verify. If you encounter return in a Bitcoin script, it stops execution and just fails the transaction. So you can use that to say never go down this path. And I never want you to go down this path. I'm going to put a return on it, and then your script will never do this dangerous thing. So these are not all of the functions Bitcoin has. These are just the ones that I most commonly use. If you want a full list of the functions that are available in Bitcoin script, you can check out this page right here. And that'll give you all of the nitty-gritty details. Okay, let's talk about some gotchas. If you're going to be developing on L1, there's some things to be aware of, some things that are unique and challenging about Bitcoin script. One of them is you can't give custom names to your variables or your functions. You can have variables and you can have functions, but you can't name them. So normally in a programming language, if you wanted to do a coin flip, you might write a function called coin flip, and you would take inputs of Alice's flip and Bob's flip, and then do something with those. But you can't do that in Bitcoin. You can write the function, and after you've written your function in a normal programming language, you would then call it wherever you want. But you can't do that in Bitcoin. You can write a function, but it's not going to have a name. It just is a list of opcodes, operation codes, or functions that you want to run. So some of the functions are all a list of built-in functions. So like you can compile a list of do check sig and then do some addition and swap some things. That might be a function in Bitcoin, or a user-defined function, but it wouldn't have a name. Just be a list of some of the built-in functions. You can, however, add comments. You can kind of get around this by adding comments to your code. So you can say, like, even though this doesn't actually have a name, from line 5 to line 200, that's all a function that I'm going to call whatever. And then your function doesn't actually have a name, but it's got a comment above it that can kind of help you keep track of where it is. You can do that with variables as well. You can just add comments above them to say what they're doing. So there are some script compilers, Bitcoin Lib and Bitcoin.js and Minsk, min.sc. That's actually a website. You can go there. And they are higher level languages that give you stuff like named variables and named functions, and then they compile down to Bitcoin script. I use Bitcoin.js all the time. Minsk is not complete yet, but it reminds me of Bash. It looks a lot like Bash, and I really like the way it looks, but it doesn't fully work yet. Bitcoin Lib is great. I use that one all the time. We're going to use it today. Another thing you can't do with Bitcoin is you can't write a function once and call it twice. So if you do a coin flip function and you want to have like 5 coin flips, you've got to copy paste your code 5 times. You've got to write that function of 100 lines or whatever, and then copy paste it wherever you want to do it. In a normal programming language, you could write it once and then call the coin flip function 5 times later on, and that would be more efficient. But Bitcoin doesn't let you do that. You just got to write a function once and call it twice, or call it however many times you've got to write a function 5 times if you want to call it 5 times. You can use these. Like Bitcoin script, Bitcoin.js lets you, like, when it compiles it, it'll paste it multiple times for you if you wanted to do that. But yeah, once it gets down to Bitcoin, it's actually written out sequentially. Another gotcha, if you ever want to do anything with big numbers, Bitcoin doesn't have very big numbers. The maximum size of an integer in Bitcoin is this. Everything above that is a string, and the maximum negative size is negative this, and everything below that is considered a string in Bitcoin. And of course, the difference between strings and integers, just like with ordinary programming languages, you can do mathematics on integers, you can add and subtract them and stuff like that, but you can't with strings. If you try to add a string to another string, it'll concatenate it instead, which is, well, actually in Bitcoin, we don't have concatenate, so it'll just throw an error. If you try to add 2 strings together, Bitcoin will be like, these aren't integers, error, failed transaction. So integers and strings must all be passed in as hex. You have to use hex a lot in Bitcoin. Bitcoin.js, as we'll see later, has some helpers for that. So it'll turn things into hex for you under certain conditions. But everything has to be passed in as hex. Bitcoin script loves hex, except for the numbers 0 through 16. The numbers 0 through 16 are special. They have their own opcodes, and those are op0 through op16. You can put those in, and then those don't get passed in as hex. In fact, if you do pass them in as hex, it's invalid. They won't work. The Bitcoin will get mad at you. Well, I shouldn't say invalid. It's non-standard, and people won't relay it for you. Okay, so those are some of the gotchas, and the last gotcha I want to warn you about is if then else, which is weird in Bitcoin script. So over here, I've got an example of how a normal programming language does if then else, and when they normal programming languages try to follow how natural language would do it. So here we've got if condition 1 happens or condition 2 happens, then you check Alice's signature. Otherwise, you check Bob's signature. This double pipe here is, at least in JavaScript and Python, that's an OR operator. I think it's pretty common for that to be an OR operator in lots of programming languages. So that's how normal programming languages follow the patterns of human speech. If you do this, then do this, otherwise do this. Bitcoin's different. Here's the equivalent version of that in Bitcoin script. And you've got a 1 and a 0, one after the other, and then op or. So already it's different. Like the two conditions actually come first before the if statement, and then you do an or after them. Like that's already weird. But then after you've figured out which condition you're using, then you run an if on it. And if it's a 1, it'll run this, and if it's a 0, it'll run this. It'll run the second one. But then we also have like Yoda speech in Bitcoin, where instead of saying, check Alice's pub key, it's like, here's Alice's pub key, now check the signature on it. Here's Bob's pub key, now check the signature on it. Like Yoda always puts the verb last, and Bitcoin script does too. We put the functions after everything else. So Bitcoin's a little different in this way. Also, in a normal programming language, condition 1 and condition 2 could both be functions themselves. Not so in Bitcoin. The only thing you can have as input to an if statement is a 0 or a 1. 1 will trigger the first condition and 0 will trigger the other one. Op or here will compare the 1 and the 0, and then if either of them is a 1, it'll result in a 1 on the stack. Or if both of them are a 0, then it'll result in a 0 on the stack, and that'll be the input to the if statement. So if then else is a little weird in Bitcoin, and you got to be aware of that when you're designing it. Everything in Bitcoin is like done with Yoda speech, where the function comes last and all of its inputs come first. So that's weird, because normal programming languages let you like have parentheses and put them as parameters, but you just have to get used to it. Bitcoin works this way. Okay, so those are some gotchas. The next thing we're going to do is we're going to design our first Bitcoin script. So hopefully you've all got Bitcoin Core running now, and let's do it. Let's make a ball game contract with each other. I'm going to do this in the browser. And I like to program in the browser because that means everyone's got a browser and you can all participate with me. And you don't have to download like a special IDE or anything. But in order to do stuff in the browser, the first thing I'm going to do is make a new folder. And then I'm going to do, I'm going to call it test contract. Well, test smart contract, that's what I'll call it. I'm going to make a folder called test smart contract. And inside, let's create an index.html file. Index.html. All right, I'm going to open that up in a text editor. You don't have to use Sublime. You can use whatever text editor you want. I'm using Sublime because I like it. You can use Visual Studio if you like. You can use Microsoft Notepad, whatever you're comfortable editing text in. And then copy the code from here, the HTML, and paste it in. And now if we open this up in our browser, we should see a blank page. And if we open up our developer console by going to more tools, browser console, we shouldn't have any errors. But there are errors. This is annoying. I think these errors are created by like extensions that I have, because I've got no JavaScript running on this page, and yet I'm seeing errors. Let me try this in a different browser. I will open this up in Chrome instead. And then maybe Chrome won't show me any errors in here. More tools, developer tools, console. Yeah, now we've got no errors. Okay, so I'm gonna go back to my slideshow. Because I accidentally closed out of it when I did that. Learn Bitcoin script. And okay, so now we've got our page open in a browser, and the next thing we're going to do is we're going to modify its head. So copy this code, paste it in where your current head is, just replace what you've got there. And we've added some libraries. We've added the Bitcoin.js library, which we're going to use because that's a really excellent tool for creating Bitcoin smart contracts. We've added the buffer library. JavaScript is kind of like Bitcoin in that integers can only be a certain size. I think it's like 4 billion or something with JavaScript, which is much bigger than Bitcoin lets you do. Whatever it is much bigger than Bitcoin. But we use the buffer library in JavaScript to let us deal with larger numbers, which you need to if you're going to deal with private keys and public keys because they're massive. And then there's variable unsigned integers for Bitcoin. This is the stupidest thing in Bitcoin, and I'm going to rant about it later in this lesson. But you need it to do something stupid, and so I'll go into that later. But for now, just pop it into your code, and we'll keep on moving. The next thing we're going to do is we're going to pop some script tags in to our code, and this is going to form the basis of our contract here. I've decided to put this code into my body because JavaScript doesn't care whether you put stuff in the head or the body. It'll run it just fine, but I want this one in my body. So what does this code do? Well, let me zoom in for you. We're going to create a variable called Alice. We're going to use Bitcoin.js to create a key pair for her, a public key and a private key. We're going to assign the private key to Alice priv and the public key to Alice pub, and then we're going to log in our console Alice's public key. Then we're going to do the same thing for Bob. We're going to create a private key and a public key for him, and we're going to log his public key. After that, we're going to create two hashes, something called the Packers hash and something called the Saints hash. Our smart contract is going to be based on a ball game. We're going to pretend there's an upcoming ball game between the Packers and the Saints, and we're going to pretend that ESPN is our oracle. And ESPN has created a secret that hashes to this value, and they're going to call that the Packers secret. Then they've created a secret that hashes to this value, and they're going to call that the Saints secret. And that's going to be effectively the third key in our contract. Alice and Bob are going to create a Bitcoin address where one of them gets to spend it, but only if they learn, Alice can only spend it if she learns the Packers secret, and Bob can only spend it if he learns the Saints secret. And we're going to use these hashes to check if they know the secret. So that's what we're going to do. Let's refresh our code and see if there are any errors. And there are no errors, but what we do get, check this out, is we get some public keys. We can see Alice's public key in here, and we can see Bob's pub key. They've both just been created. Awesome. So things are working. Things are actually running fine. I was worried when it didn't work earlier, but I think it was just an extension was throwing some kind of error. So doing it in this browser is better. The next thing we're going to do is we're actually going to create our script. So let me do this, and we'll pop that right into here, a new script tag. This is the ball game script. It's going to take Alice's pub key and Bob's pub key as input. It's going to take both of these Packers hashes, and it's going to create a Bitcoin script for us. And this Bitcoin script says, if we take our secret and hash it, and it matches the Packers hash, we're going to check that they match with op equal verify, and then we're going to let Alice spend the money. We're going to have her pop in her signature and check that it's valid. And as long as she provides a valid signature and she knows the Packers hash, she gets to spend the money. Or if we trigger the else condition, then we're going to take the secret provided by Bob, check if it's equivalent to the Saints hash, and if it is, then we're going to check Bob's signature and allow Bob to spend the money. And then we're going to end. We're going to end the script because that's all it does. It just says if you know this secret, Alice can spend the money, or if we know the other secret, Bob can spend the money. And then an oracle, ESPN, can provide the secret. So that's how our ball game contract is going to work. Now we've got it in script format. All we've got to do now is run it right here, and we should see our smart contract pop out in our console. So here we go. Pop in this code. Let me indent it. I like things to be indented properly. Yeah, we're creating a function called ball game, which is going to create a pay to witness script hash script. That's one way to do scripts in Bitcoin is with pay to witness script hash. It's type of Bitcoin address. We're going to create this address by calling our ball game script, which is just going to create this function, create this Bitcoin script function, and turn it into a Bitcoin address. And then we're going to log that Bitcoin address, return the pay to witness script hash address. So let's just run this. When we run ball game contract, we're going to pass in all these variables that we created, up here, and we should see a smart contract address come out. Let's refresh our page, and there it is. There's our Bitcoin smart contract. This Bitcoin address, if we send any money to it, Alice will be able to spend it if she learns the Packers secret, and Bob will be able to spend it if he learns the Saints secret. So we're going to do that. We're going to send some money to this, but I do want to show you what happens if we refresh. Notice that the address ends in 6MQVSA. If we refresh, it changes to XF7CZ. And if we refresh it again, it'll change again. Every time we refresh this page, the smart contract changes. This is different from if you're familiar with working in something like Ethereum. Once you've made a contract in Ethereum, it stays the same. And that's because you put the smart contract on the blockchain, which doesn't change. confirmed blocks never change. And so the smart contract address stays the same every time. In Bitcoin, we do things differently. We're putting Alice's pub key and Bob's pub key. They're part of this smart contract. You can actually see right here, Alice pub, Bob pub. And because their public keys are part of this, every time I change their public key, the smart contract changes because it includes their public keys. So every time I refresh, I'm not saving their public keys anywhere. It's just making new ones for them every time. And consequently, the smart contract changes every time. Okay, so we're about to send some money to this, but I want to go over how Bitcoin's stack works. Before we actually run this program, I want to show you a visual representation of Bitcoin's virtual machine and how it operates. Okay, so this over here is going to be, I think of it as a bucket. This is actually a stack though, and we're going to take items from our art. We're going to take items from the arguments section, pop them into the stack, and then run our program on them. But the virtual machine has a set of operations that it uses. And the current operation, whenever you start a Bitcoin script, its current operation, the first thing it does is it checks the arguments section and tries to find any strings or numbers that are on this stack. And if there are any, it's going to pop them into this stack over here, which is the execution stack. So we'll just see that it says, okay, I looked in arguments, I found a signature, so I'm going to pop that signature into the execution stack. The next thing it's going to do is it's going to do that again. It's going to look in the argument section, check if there are any strings and numbers. It found pub key there, and so it puts pub key onto the execution stack. The next thing it does, well, there are no strings or numbers anymore in the arguments section. So it's going to move up to the program section and look there. Well, there are no strings or numbers up here in the program section either, but there is a function. There's a dupe function. So the next operation the virtual machine does, if there are no strings or numbers here or here, then it's going to run a function, if any. So it finds a function called dupe, and it's going to put dupe into the current operation. What does dupe do? Well, dupe takes one element from the stack, that's the pub key in this case. It's going to copy that, and it's going to put both copies onto the stack. So it pops in pub key onto here. It's going to copy pub key right there. So now there are two pub keys, and then it's going to put both of them on the stack. That's what dupe does. Now it's done with dupe, so it's going to go back to its regular mode of operation. Check the arguments, see if there are any arguments here, strings or numbers, put them on the stack. There are none. Move up here to the program. Are there any strings or numbers? Nope, there are no strings or numbers. So then, if there are no strings and numbers, run a function. Well, there's a hash function. So it's going to pop the hash function down into here. What does the hash function do? It takes one element from the execution stack. That's this public key. And then it's going to hash it. It's going to turn it into key hash. And it's going to put the key hash onto the stack where the pub key was. That's the hash function. Now it's done with that. Move back to your regular mode of operation. Check if there are any strings or numbers in the arguments. There are none. Check if there are any strings or numbers up here. There is one. There's the phrase key hash. That's up here in the program. So it's going to pop key hash onto the stack. Then it goes back to its regular mode of operation. Check if there are any strings or numbers in the arguments section. There are none. So it goes up here. Check if there are any numbers or strings up here. There are none. Okay, then it's going to run a function if there is one. Well, there is one. There's equal verify. So what does equal verify do? It checks if two elements are the same and fails if not. So it takes both key hashes and checks if they're the same, and it fails if they're not. Equal verify is actually a combination of two functions. Equal is one function in Bitcoin, and verify is another. So if we were using them separately, if we were using equal and then verify, it would check if these two things are equal, and then it would put a 1 on the stack, and then the verify function would just check if the top element is a 1, and if it is a 1, it will continue, otherwise it will fail. But we actually combine those into equal verify one function, which just checks if two things are equal and fails if they're not. But in this case, they are, so they're consumed, nothing's put on the stack, and we just continue. Check if there are any strings or numbers here, there are none. Check if there are any strings or numbers here, there are none. Okay, so we'll run a function called checksig. Checksig takes a signature and a public key as input, checks if the signature is valid for that public key, and returns a 1 if they are. So it'll put those into the current operation, check if it's valid, and if it is, if they are, in this case they are, so it'll put a 1 on the stack. Then it goes back to its regular mode of operation. Check if there are any strings or arguments. There are none here. Check if there are any in the program. There are none there. then if there aren't, then run a function, if any. But oh no, there are no functions in the program. So the program has terminated. And once the program terminates, all that needs to happen is if there's a single one on the execution stack, the program succeeds. So there is a single one there because our checksig put one there. So the program will succeed. If it was anything else, it was a 0, for example, the program would fail and would not go forward. So that is how Bitcoin's virtual machine operates. It's a loop. It just keeps on checking for things here, and running any functions it sees until it's finished. And then it wants there to be a single one on the execution stack, and that'll make it work. Okay, so that is what our function, our simple little if-else function's got to do. It's got to end up with just a single one on the stack. Last thing is the part where I rant. That we've got a function here called witness stack to script witness. And I do not like this function. I'm going to pop it directly into my console and hit enter. And let me tell you what this witness stack to script witness thing does. It is terrible. This uses the variable unsigned integer that I told you about before. In Bitcoin script, whenever you put something on the stack, you have to say how long that thing is. If it's a hash, for example, that's always 32 bytes. So you have to prefix 32 bytes before whatever it is that you're running. Bitcoin.js will do that for you in most cases, but there's one thing it won't do on its own, which is the entire script. Your entire script, you have to say how long that is. And Bitcoin.js won't do that for you. So we have this function called witness stack to script witness, which does that. And since your script can be a variable size, it has to be a variable unsigned integer. And it'll pop that onto the thing. And I just hate this. Like Satoshi was such an engineer who wanted to be so precise about everything. Like, let's make sure you specify how long everything is, and let's specify even how long the script itself is. Just a madman. Anyway, I don't like this function because it's ugly and it's horrible, but you need it. And so you just pop it into your code and it'll tell you how long your script is. Okay, so we got that in there. Now we have to run our function. And so the execution of a script in Bitcoin is a bit longer than the creation of a script, but we're going to do it. So I'm going to take it's in 5 parts here. And so we'll pop all of this into our console, and don't hit enter because there's more to it. But the first thing we're going to do is we're going to take a transaction ID from Bitcoin Core after we've sent money to our smart contract. We're going to take a transaction index. We're going to find out what address the money is in, or not what address the money is in, but where we want to send the money. We're going to define all those variables. We're going to say how much money is in the Bitcoin address, how much money is going to go to Alice or Bob or whoever's winning. And then we're going to get the witness script. We're going to get the actual script. We're going to recreate the ballgame script because you need to recreate your script in order to spend it. Okay, so that's what that part is going to do, but that's just part 1. The next one is part 2 of this. And so let's pop that in, and then I'll tell you what it does. Part 2, it uses the witness script to recreate the Bitcoin address that has the money in it, because you need to know what address you're spending out of. And then it creates something called an output script, which is just how Bitcoin decodes a witness script and turns it into something it likes. And then part 3 creates something called a partially signed Bitcoin transaction. Partially signed Bitcoin transactions are a format for working with Bitcoin transactions that was designed originally for when you're going to do multi-sig. You can use this transaction format to pass around my signatures, and you can give me yours, and we can come to consensus on a transaction. In this case, we're not exactly using multi-sig, but it's useful anyway to just have a common standardized format for passing around Bitcoin transactions and signatures. So we're using it. So we're putting all that information into PSBT format, and then we're just going to add an output to our PSBT, which is going to be Alice's address or Bob's address if he wins. That's going to be the output, and then we're going to put however much money he's winning is going to go into there, and then we're going to sign it. We're going to sign it with whoever wins private key. And then lastly, the last part of this thing is called get final scripts, and the get final scripts function, all it does is it takes everything that's on your stack, uses the variable unsigned integer thing to say how long everything is, which it does down here, and then returns your final script. And that's all we need. Then that'll give us a signed Bitcoin transaction, right here, extract transaction, that we can then broadcast to the network. So that's our function, and we just hit enter, and there it is. Our function is all ready to call. All we need to do now is actually send some money into that address and then withdraw it. So let's go up to our Bitcoin address. Our smart contract Bitcoin address is right here. Pull that into Bitcoin Core, right here. We're going to send some money to it, and we will send, how much money did I say was going to be in there? I believe I said something like 25 million sats. Yeah, right here. Original quantity of cents is going to be this. So we will send that amount of money into the address. And we'll have a fee of 1 sat per byte. So, yep, we will send this in. So we've got some money in our little Bitcoin, our testnet Bitcoin address, 25 million sats. And we need a couple of pieces of information from this. So show transaction details. We need to know the transaction ID, and we need to know the VOUT. So we can pop that into our function because Bitcoin needs to know these things in order to spend money. So we'll just pop our transaction ID right there. And well, we need the TX index, which we can get by going into we got its transaction ID, so I can go into my console window, open the console, and say get transaction, paste false true. And we can see in here that it is output number 1. There are 2 outputs. We spent the change back to ourselves, and we sent 25 million sats into the address. So we will take the index number 1. And this is going to be the winner's address. So all we're going to do now is call this, this function using our last bit of code here, withdraw from ballgame address, and we should see a successful transaction. So here's the secret. This is the secret that says the Packers won. And then we're going to pass in Alice's private key, which we already defined earlier. And we're going to pass in these other functions that recreate the Bitcoin address. And when we do, we get this. We get a Bitcoin transaction. And if we just copy that into Bitcoin, right, into our console, we say send raw transaction. There we go. We just sent that raw transaction. And here's the transaction ID that moved the money over to Alice. So we have created and run a Bitcoin smart contract. This secret is the one for if the Packers won. If you want to change it, you can make it that. We just changed the last letter to a C. That is for if the Saints win. And then you can have Bob get the money by putting in Bob's private key here. And the other thing you need to do is instead of passing in a 1 that triggers the if condition, you'd pass in a 0 right here, and that would pass in the else condition where Bob wins. And then you'd run your script again, and Bob would win this time. But as is, we made Alice win. She won the game, and ESPN would reveal this secret, or probably a much more secure secret for whichever team won. But that's how you can build an oracle in Bitcoin. I certainly recommend, lastly, if you want to try out more scripts, you can make your own using the ScriptWiz IDE. Just go and change it over to Bitcoin from Liquid, and then you can experiment away with writing Bitcoin scripts on your own. And lastly, I have my references. So in preparation for making this course, this lesson, I read Nick Szabo's smart contracts paper. I read Andreas Antonopoulos' wonderful book, Mastering Bitcoin, which tells you how to use, which tells you how to do all this stuff in more detail. He also has a wonderful YouTube video called Advanced Bitcoin Scripting, where he shows you how to make really complicated scripts similar to the ones I've done here. And then there's a Bitcoin wiki, which gives you a list of all the scripts that all the functions Bitcoin script has, and what you can do with them and how they work. So all of that is more detail, but we've got three minutes for questions and comments. So let's go see if there are any. And yeah, I'm going to stop sharing my screen now. So,
I was just about to say, I saw Rafa's hand up. Rafa, go for it.
What's up, Rafa?
Hey, Super Testnet.
Can you guys hear me? Thank you, James. Actually, I had a question at the beginning. If you could walk me through the, was it the swap, like at a high level, like the swap or the tokens use case that I know you explained it, but like step by step, like at the high level. And this was fantastic. Thank you.
You're welcome. You're welcome. Yeah. So a swap is the way we used to do swaps in Satoshi's day was that you'd have two blockchains. He did this on Namecoin, I think was like the only other blockchain when Satoshi was around was Namecoin. And so he proposed, I think this is how it worked. You'd create a multi-signature Bitcoin address and a multi-signature, I forget if it was Bitcoin or Namecoin. On one of them, you'd create a multi-sig. And you would make it so that you'd create a corresponding address on the other chain, where in order to spend from the address on the other chain, you would have to reveal your private key on the original chain. You'd have to like put it in as input to the script. And so then when you've done that, by revealing your private key, it would make it so that the other person would have both private keys that he needs to take the money from the other chain, to take the money from the address on the other chain. And so that's how it worked. Basically, you create two Bitcoin addresses. One of them would require you to in plain text show your private key for the other chain. And once you've shown that, your counterparty, you get that money. You get to spend the money by putting in your private key, but your counterparty now has both of the private keys he needs to spend the money on the other chain. So you could use that for an atomic swap. You put money in address A and address B, and then if you give your private key on this chain, he gets the money on the other chain. You get the money on chain A, he gets the money on chain B.
That's crystal clear. And then the other use case, was it like the token use case that you presented at the beginning?
Yeah. Well, ordinarily there are a variety of methods for marking a Bitcoin address as special and then treating the sats in it as special. The latest example was ordinals, where we keep track of how early some Satoshis went into an address on the chain, and then that earlier addresses are special, or earlier coins are special. So that's one way of doing it. We also have a function in Bitcoin called op-return. And since I just ran out of time, I will just say you can learn more about creating tokens on Bitcoin, like classical ways of doing it. If you want to learn like the history of this stuff. What's it called? Omni. Omni. Look up Omni, Omni blockchain, or look up Omni Bitcoin. It was an early protocol for doing this using a function in Bitcoin called op-return to mark an address as special and then treat the sats in it as tokens, tokens other than Bitcoin. Yes, colored. Someone in the comment section says colored coins. Basically, yes, that was at the time they were called colored coins. So that's classical versions of how tokens work. I'm sorry to say that I'm out of time. My presentation ran long and I didn't have time for questions. So sorry, everybody, but it is time for the next person to present.